Good morning, everyone. Uh, Thank you for attending the 18th Conference on Quantum Information Processing, QIP 2015. This year's workshop conference is jointly organized by University of Technology Sydney, UTS, the University of Sydney, Macquarie University, and the University of Queensland. The local host is UTS, the Center for Quantum Computation and Intelligent Systems. So now let's welcome Professor Ming-Shen Ying, the General Conference Chair and the Research Director of QCS, to deliver a welcome speech.
Good morning, everyone. So welcome to the QIP 2015. So it's my great pleasure to say a few words to open this conference. As you can imagine, there are so many people contributed to the successful organization and the running of the conference. We have very wonderful scientific programs. So first of all, I'd like to thank the steering committee and the program committee for producing this really wonderful programs, including tutorials, panelist talks, contributor talks, and also poster session. I also like to thank the authors of all submissions for their contribution to the conference. Secondly, we are very grateful to the local organizers from UTS, University of Sydney, and Macquarie University for their hard work. In particular, I like to mention Lun Yao, Michael, Ming-Shu, and Ms. Li Liu for their amazing devotion to the conference. Since this conference is hosted by the UTS Center for Quantum Computation and the Intelligent System, so please allow me to give a very brief introduction to this center. So this center was founded in 2008. It consists of two parts. One is quantum computation. The other is intelligent system, so artificial intelligence. On the quantum part, we have people working on the algorithms and the complexity, programming languages, and also information theory. On the AI side, we have people working on machine learning, data mining, and decision making. So we are also exploring the possibility to combine quantum and AI. So I hope QCS will have opportunity to cooperate with you after the conference. Thank you. So enjoy the conference. Thank you.
Thank you, Professor Ying. And because time is very short, so allow me to do one last thing. This is something I have to do. So these are all our sponsors. With their sponsorship, we are able to sponsor more than 40 students and young postdocs to this conference. So they are all host university, all organized universities, including this LC Center EQUS, and also Sandia National Laboratory, New South Wales Government Department of Trade and Investment, and the CQT, IQC, and this ONRG, right? And also this AI, JMP. Everyone knows this journal, and the JPA, mathematical and physics, okay, and the Spring. Okay, so let's thank for their sponsorship, and I hope you enjoy the conference and enjoy your stay in Sydney. Now, let me hand the microphone to the program chair, Rolando. Thank you.
Okay, thank you very much, Runyo. So let's start with the science. We'll have, let's say, every morning and every afternoon, we'll start with a plenary talk. And the first plenary talk will be given by Ran Ras. And for those of you who are in, let's say, classical computer science, in particular complexity theory, you will know Eran Raz. He's one of the stars of that field. And to the extent that there has been any progress in the last 20 years on lower bounds, much of that is due to Eran Raz. Things like circuit lower bounds, communication complexity. And today he's going to tell us about delegating computations.
Thank you. Let's see that it works. Oh, no. Okay. Okay, so thanks a lot. I will talk about, the title is How to Delegate Computations, the Power of No Signaling Proofs. It's a joint work with Yael Tauman-Kalai from Microsoft Research and Ron Rothblum from the Weizmann Institute. And the starting point and the main motivation for this work came actually from cryptography, and it's the problem of computation delegation that has become a very central problem in modern cryptography. So what is this problem? Suppose that Alice has an input x in 0, 1 to the n, and Alice needs to compute some function f of x. It's very important for her to compute the function, but she doesn't have sufficient computational power to do that. Now Bob has sufficient computational power to compute f of x, and he offers to compute f of x for Alice. So Alice sends x to Bob, Bob sends back f of x, and everybody is satisfied. And this situation happens today many times. Today there are many services that are called cloud platforms that offer to do all your computations for you on the web. And many companies don't really have strong computers. They just have weak computers, and they delegate all the computation to some of these, to one of these cloud platforms. Or Alice can be a weak device like a cell phone that wants to do GPS navigation and delegate it to some website. Or if the cell phone runs out of battery and wants to save on battery life to avoid further frustration. So what if Alice does not trust Bob? Sometimes the cloud platforms are malicious, or sometimes they are not malicious, but they are buggy, they have bugs, they have viruses. Suppose that it's very important for Alice to have the computation done correctly, and she wants some guarantee that the computation was done correctly. And the question is whether or not this is possible, assuming that Alice doesn't have the computational power to do the computation herself. So this is the problem of computation delegation, and we will get back to Alice and Bob later on. But meanwhile, let me tell you about the amazing breakthroughs in engineering on Mars. So the Martians are amazing engineers. A quantum computer was built in their prehistory. They build iPhones in kindergarten as an exercise, and then in school they moved to Android. And last week, a group of their best engineers from the Martian Institute for Technology, the MIT, announced the strongest and most amazing computer of all times. They call it the EXP time machine. It does every computation that can be done in exponential time, it does in 1 second. So this is the amazing computer. And of course, us in Earth, we want to delegate all our computations to the Martians, since they have this amazing computer. In particular, if we have some really important computation that we want to do and we don't have sufficient computational power, we want to delegate it to the Martians. But of course, the problem is, as before, that we don't trust the Martians. And the question is whether or not they will be able to convince us that the computation was done correctly, assuming that we don't have enough computational power to do the computation ourselves. So this is, again, the same problem. And of course, one thing that the Martians can do is to write a mathematical proof that the output of the computation is correct. But typically, if the computation take time t of n to compute, then this proof will be of length t of n, or O of t of n. So just to verify this proof will take the same amount of time as to do the computation ourselves. So it's practically the same thing, so it doesn't help much. So people thought about these problems for a long time, and they came up with some amazing suggestions of how to do that, of how to convince someone that the computation was done correctly. And let me tell you about the multi-prover interactive proof model. Actually, two of the suggestions were interactive proofs and multi-prover interactive proofs. And this slide is about the multi-prover interactive proof model of Ben-Or, Goldwasser, Kilian, and Wigderson, probably from around 25 years ago. And here I only present the two-provers model, but of course it can be generalized to k-provers model for any k. So roughly speaking, in this model, we have three parties. We have two players, A and B, that we call the provers, and we assume that the provers are infinitely powerful. They can compute anything immediately. Each of them has like the X prime machine, or they have infinite computational power. We have another party that we call the verifier. And roughly speaking, in this, what happens here, the two provers try to convince the verifier that a certain mathematical statement is true. So in this case, the statement is that X is in the language L. That's how we write it in computer science usually. For some language L, we want the provers to prove that X is in the language L. So the proof goes as an interactive protocol between the verifier and the provers. The verifier V sends one query Q to A, to the first prover, and one query R to the second prover. And the Q and R are chosen based on X. X is known, everything is known, like the provers and the verifiers know X and L, and based on X, the verifier chooses Q and R and sends Q to the first prover and R to the second prover. It's very important that there is no communication between the provers. The provers are placed in two different rooms. And the first prover A answers by some answer A that is only a function of Q, and the second prover B answers by an answer B that is only a function of R. So there is no communication between them, and each of them doesn't have any information about the input of the other. Now, based on this interaction, based on Q, R, A, and B, the verifier decides whether to accept or reject the assumption that X is in L, that the mathematical statement that we try to prove is true. So if the answers seem correct, the verifier accept, and if not, the verifier reject. So that's how it goes. Now, what makes it a proof? What makes it a good proof system? What makes the proof convincing? This is just a protocol between the provers and the verifier. So we usually require the standard completeness and soundness requirement, and this will be what makes the proof convincing. So we have the completeness assumption that if the provers A and B are honest and the mathematical statement is correct, so if X is in L, if the mathematical statement is correct and the provers are honest and behave according to the protocol, then the verifier will always accept. So the completeness is 1, and so this means that if there is a known proof that they know, they can actually follow this proof and convince the verifier that actually the proof is correct. The second condition, that this is what makes the proof convincing, is the soundness. You don't see the last line, so I will just read it. So the soundness says the soundness is the most important property that makes the proof convincing. The soundness says that if X is not in the language, if the mathematical statement that we are trying to prove is not correct, then no matter what the provers will do, they can be cheating, they can do anything they want except communicating with each other, they will not be able to convince the verifier. So the line that you cannot read is that the probability that V rejects is 1 minus negligible. So if the statement is not true, if X is not in L, then no matter what the provers will do, the verifier will reject with probability very close to 1. And this is what makes the proof convincing, because the verifier knows that if he accepted, then with very high probability, the statement is really true. And this is an amazing idea, this proof system, the two-prover interactive proofs model or multi-prover interactive proofs model. I would say it's one of the coolest ideas of all time, and it had amazing influence. And what made this model very influential is that there are actually very good multi-prover interactive proofs for practically all languages that we want to talk about. And this is the result that MIP equals X, multi-prover interactive proof with polynomial size that all the interaction is polynomial, can do non-deterministic exponential time. And this is an informal presentation of this result. Any mathematical statement, take any mathematical statement that you can write in length n, and that has a proof of length t. So you should think of t as much larger than n, say even exponential in n. So the mathematical statement is of length n, the proof is of length t. So such a proof can be verified by a two-prover interactive proof with more or less polylogarithmic resources. So there is a convincing two-prover interactive protocol that will convince the verifier that the mathematical statement is correct, and the running time of the verifier will be n times polylog t. N is the time that takes to read the mathematical statement, and only polylogarithmic in the length of the original proof. So even if the original proof was exponential, this will be polynomial. And also the communication, the query, the length of the queries and the length of the answers of the provers will be polylogarithmic in t. So this is more or less the MIP equals NEXP result. This is informally. So again, it means that if you have a mathematical proof, even of exponential length, you can convince a verifier by the validity of this proof by only polylogarithmic resources, with communication that is only polylogarithmic. So this is the result. This is a more formal presentation of the same result. Maybe I will skip it just to save time for later on. It says the same thing. So it says that for any language in non-deterministic time t of n, there is a multi-prover interactive proof with the completeness and soundness that we want. Actually, here you can see the soundness that you missed last time. The probability that V rejects is 1 minus negligible. And the resources are polylogarithmic times n. Okay, so this is the MIP equals NEXP result. And using this result, the Martians can convince us that the computation was done correctly. We take two Martians, we put them in two different rooms that they cannot communicate, and we send a query, one query to one Martian, and one query to the other Martian. The queries are only of polylogarithmic length. The Martians answer by answers, also of polylogarithmic length. And if they answered correctly, if they answered what seems to us correctly, we know that their computation was done correctly because of the soundness assumption. So we can use this protocol, the Martians can use this protocol to convince us that the computation was done correctly, and the resources are polylogarithmic in the length of the original computation, so we don't need high computational power. And one comment is that the requirement of no communication between the provers, between the Martians in this case, can be guaranteed physically by special relativity, because you can take the Martians and put one Martian on one planet and another Martian on another planet, stand in the middle, send them the query, and expect the answers to arrive so fast so that they cannot communicate by the speed of light in between. So this way you can guarantee that the Martians did not communicate, and you are convinced that the computation was done correctly. Or at least so was the situation until QIP 2004. And in QIP 2004, 11 years ago, Cleve, Hoyer, Toner, and Watrous asked, didn't we forget something? And of course, in this forum, is of course what we forgot is that maybe the provers can share quantum entanglement. And maybe if the prover share EPR pairs, they can cheat us, like in the EPR paradox, that they can do better if they share EPR if they share EPR pairs. And indeed, in many protocols, the provers can do better if they share EPR pairs, if they share entangled quantum states, and they can cheat us and prove something that that is not correct. We will not have the soundness. So more formally, we define entangled strategies as the following strategies. So again, the protocol is as before. We send Q and R to A and B, and we get answers A and B. Q, R, A, and B are classical. But A and B, the provers A and B, share an entangled quantum state. S that is partitioned to A's part and B's part. Now, the prover A got the query Q, the question Q, and before A answers the query, A measures his part of the state S, and based on the result of the measurement, answers by the classical answer A. And prover B does the same. Before prover B got the query R, and before she answers, she measures her part of the state and answers by B. And this way they answered by answers A and B that might not be possible to implement by classical protocols. And these are entangled strategies. And we want our protocols to be sound even for entangled strategies. So we want the protocol to be such that for any entangled cheating provers A and B, if X is not in L, if the mathematical statement that we try to prove is not correct, then V will reject with probability close to 1. So this is the soundness against entangled strategies that we wish for. And this was open for a long time. And two and 3 years ago, there was a result by Ito and Vidic, and then an improvement by Vidic that actually closed this open problem. So what they showed is a good multi-prover interactive proof for NEX, exactly the same result as before, but with soundness against entangled strategies. And this is a really, really nice result. But they do it with 3 provers rather than 2. So this is not that important. They do it with 3 provers, but it's still open whether or not you can do it with 2 provers. So more or less, the result is the same as before. I will just read it again. If you have any mathematical statement of length n that has a proof of length t, and again think of t as larger, much larger than n, say exponential, there is a through-prover interactive proof that will convince you that the proof is correct, that the mathematical statement is correct, and the parameters are the same as before. The running time of the verifier is n times polylog t. N is relatively small, so it's polylogarithmic in the length of the original proof. And also the answer size and the question size are polylogarithmic in t. So the interaction is polylogarithmic. So this completely solves the problem, assuming that the population of Mars is larger than 2. Okay, so this is the soundness for entangled strategies. And what I will talk about today I will talk about an even stronger soundness assumption. And this will be soundness against no signaling strategies. So no signaling strategies are more general than entangled strategies. They include all the entangled strategies, but they include also many additional strategies. And no signaling interactions were studied in physics for a long time. No signaling multi-prover interactive proofs were studied since the paper of Cleve, Hoyer, Toner, and Watrous that I mentioned. So more or less informally, the no signaling strategies are all the strategies of the two provers that cannot be used to pass information between the two provers. This is informally, but there is a very simple mathematical condition for no signaling. And this is the mathematical condition for no signaling. So what are the no signaling strategies? Again, we have two provers A and B. Prover A get Q, prover B get R, and prover A answers by A, prover B answers then B. How do they answer? So now we allow both provers to see both queries. Okay, so prover A sees both Q and R, and prover B see both Q and R, and each one of them also has an access to a common random string, to a shared random string that we call Z. So the answer of prover A should be a function of Q, R, and Z, and the answer of prover B should be also an answer of Q, R, and Z. So far, everything is possible. But there are two conditions that we call the no signaling conditions. And this is the first condition and the second condition, one condition for each prover. So the first condition is for prover A that given conditioned on the query Q, the random variables A and R are independent. So conditioned on the query for the first prover, the answer of the first prover is independent of the query of the second prover. And we have another condition for the second prover. Conditioned on the query for the second prover, the answer by the second prover is independent as a random variable of the query for the first prover. This is the no signaling this is the no signaling condition. These are non-signaling strategies. This is the simple mathematical requirement. It can be also generalized to the K provers case, and this is the generalization. I will read it, but it's not so important for this talk to understand it exactly, although it's simple. So suppose that we have K provers that get queries Q1 to QK, and they answer by A1 to AK. Now the requirement is, so each answer AI can depend on all the queries Q1 to QK and a random string Z, exactly as before. So each prover can see all the queries and a random string. And the requirement that we have is that for every subset S of provers, given the queries for these provers, for the provers in the subset S, the answers of these queries, of these provers, are independent of all the queries for the other provers as random variables. So again, if we condition on the queries for a subset of provers, the answers of that subset of provers is independent as a random variables of the queries for all other provers. So this is the no signaling strategies for K provers. And what we want is that our protocols will be sound even for non-signaling strategies. So we want that for any no signaling strategies, A1 to AK if X is not in L, if the mathematical statement that we try to prove is not correct, then the probability that V rejects is very, very close to 1. So V will not accept an incorrect statement even if the provers apply no signaling strategies. This is the no signaling soundness requirement that we want. Okay, so now what's the connection between entangled strategies and no signaling strategies? So as I told you, all entangled strategies are no signaling. And this can be proved easily mathematically, but there is of course a strong physical reason for why this is true. And the reason is that signaling strategies means that information passed between the two provers. And this happens instantly. So if the provers apply signaling strategies, information passed between them instantly, faster than light. And in physics, you cannot pass information faster than light, because if information passes faster than light, then in a different Lorentzian system, it went from the future to the past. So this is a problem with causality. You don't want information to pass from the future to the past. This is the principle that all the stock markets are based on. So therefore, all entangled strategies must be no signaling, and actually all the strategies that you can expect in real life must be no signaling. So it's possible that there will be a future ultimate theory of physics that will allow other strategies, not only entangled strategies, but if you have soundness against no signaling strategies, then you ensure that even in these future theories, the provers will not be able to convince you that a statement is not correct is correct. Well, great. So we want to prove soundness against no signaling strategies, and people actually tried to do that for a long time and studied this model for a long time, and let's see what they got. Of course, the first instinct would be to take some multi-prover interactive proof for, let's say, non-deterministic exponential time, like one of the two provers proof or multi-prover proof that we talked about before, and to try to prove soundness against no signaling strategies. But this doesn't work. Actually, if you consider the class of all languages that have multi-prover interactive proofs of polynomial interaction that are sound against no signaling, I call this class no signaling MIP. Again, it's classical multi-prover interactive proofs of polynomial size that are sound against no signaling. Then it was known actually before our result that this contains p-space and is contained in exp. And if you only limit yourself to two provers, it is actually equals to p-space, and this is a result by Ito. So the more important for us is that this no signaling MIP are contained in exp. And therefore you cannot just take one of the known multi-prover interactive proofs for NEXP, for non-deterministic exponential time, and hope that it will give you no signaling soundness, because no signaling soundness immediately places you in exp and not NEXP. And therefore you need some new methods. You cannot really hope to do that by one of the known construction. Let me give you another example that shows how strong no signaling strategies are. So consider the case, again, with a verifier and two provers, and the verifier sends a query Q to one prover and a query R to the other prover. And consider the case that the verifier that the answer by each prover is 1 bit, and the verifier only checks that A the answer A XOR the answer B is equal to some constant, either 0 or 1, that depends on both Q and R. Suppose that this is the only thing that the verifier checks. We know that such proof systems in the classical soundness are very powerful. Actually, there are such proof systems for NEXPs. Actually, the results that I talked about before, you can do it actually with verifiers of this type. But there is a simple no signaling strategy that cheats the verifier with probability 1. And this is the no signaling strategy. Choose Z to be a random bit. B will just be Z, so the second prover will answer by that random bit always. And A will be VQR XOR Z. So A XOR B equals VQR, and the verifier is always convinced. On the other hand, it's a no signaling strategy. So both requirements, it's really easy to see that they hold, because conditioned on Q and R, A is random, and also conditioned on Q and R, B is random. And therefore, you satisfy both requirements of the no signaling strategy, and this is a no signaling strategy that cheats the verifier with probability 1. So this seems like a restricted case, but actually something similar can be done in many, many multi-prover interactive proof systems. So what can be done is that the two provers will see both answers and will answer by a random answers that satisfy the verifier. And many times this strategy will be no signaling and will break the proof system, will convince the verifier that an incorrect statement holds. Okay, so what is our result? Our result is that multi-prover interactive proofs of polynomial size with no signaling soundness exactly equals to the class of complexity exp. So the hard part of the result is actually one side was known before, but the hard part is to give multi-prover interactive proofs of polynomial size for exp, for the class of complexity exp, for exponential time, that have the no signaling soundness property. So this is the result more formally. For any language L that can be computed, for which membership can be decided in time t of n, so any computational problem that takes you times t of n to compute, there is a no signaling multi-prover interactive proof for membership in that language that has soundness against no signaling strategies and has the following properties. So the multi-prover interactive proof has soundness against no signaling strategies, so no one will be able to cheat even if you apply no signaling strategies. And it has the following parameters. The number of provers is polylogarithmic in t of n. So if t is exponential, k is polynomial. The communication is also polylogarithmic. The completeness is 1. The soundness, as I said, is against no signaling strategies with negligible error. The running time of the verifier is n polylog t of n, as before. And the running time of the provers, this is something that I didn't talk about before, will be poly in t of n. So also the provers don't run in time much larger than the time that it takes to decide to compute the original language. So the provers run in time poly in t of n, where t is the time that takes to compute the language L. So this is the result. And using this, you can delegate the computation to the Martians, and they will not be able to cheat you, even if they apply no signaling strategies. You just need many Martians, a polynomial number of Martians. So for any language L, any computation that they can do in time t of n, you will take a polylogarithmic number of Martians, and you place them in different places so that they cannot communicate. You send them the queries, you get the answers back, and your running time is very efficient, n times polylog t. Their running time is polynomial in t. And you are able to be convinced that the computation that they did was done correctly, even if you allow them, they cannot cheat you even if you allow them to use no signaling strategies. Okay. Meanwhile, on Earth, everybody is still frustrated. So typically, on Earth, we delegate a computation to one cloud. We have one prover. We cannot tell Amazon, okay, you run it on 2 different computers in different rooms and that that are not connected to each other. They're both connected to the internet. You don't know what happens. So there is only one prover, and we don't trust it. So what do we do? So at 2000, there was an approach of Aiello et al. To reduce the number of provers from any number to 1. And this approach uses cryptography, and it will work only under the assumptions that the provers are limited computationally. So it will, actually the provers will not be able to cheat you only if they are limited computationally. This is what we call computational soundness. So the approach is more or less the following. So it can be done for any number of provers, but I will present it here for 2 provers just for simplicity. So suppose that we have the same interaction as before. We have a verifier that sends Q and R to 2 provers and get the answers A and B. Now what we will do, we will have only one prover that we will call P. The verifier V will send both queries to the prover P. But of course, this doesn't work. You cannot send both queries to the same prover. Then the prover will know both queries and can cheat. So what you do, you send both queries to the same prover, but encrypted. So you encrypt Q and encrypt R and send Q encrypted to the prover, and you send R encrypted to the prover. But now there is a problem. The prover gets the query encrypted. How can the prover answer the query? So the point is to use a new magic in cryptography that is called fully homomorphic encryption. So the encryption that you use is of a very special type that is called fully homomorphic encryption. And the mechanism of fully homomorphic encryption allows a person that only gets the encryption to apply a function underneath the encryption. So the prover will get the query Q encrypted, and the prover will be able to apply A on Q underneath the encryption and get the encryption of the answer A hat. Hat is just means encryption. So the prover P will get both Q and R encrypted by fully homomorphic encryption and will answer by A and B encrypted. And this works only because we use the fully homomorphic encryption that allows to do that. And now it seems that this should work, that this suggestion should work and should reduce the number of provers from any number, or in this case from 2, back to 1. Why? Because the prover P got both queries, but it got it encrypted. So when the prover answers the query Q, he doesn't know what was the query R. It was encrypted. So it seems that this should work. Of course, all this is conditioned. It should work only if the prover is not able to decrypt these queries, because if the prover is able to decrypt, he knows both queries and can apply many, then he can cheat because he knows both queries. So it's all conditioned that the prover P is now computationally bounded. So we limit the computational power of the prover, so the prover cannot decrypt the query and get the queries Q and R. So it seems that this suggestion should work, but no one knows how to prove it. And what we were able to do is to connect it to no signaling soundness and to prove that this suggestion actually works if you have the no signaling soundness guarantee. So if your original multi-prover interactive proof system was sound against no signaling strategies, then this suggestion works and you can reduce the number of provers from many provers to one and use it in real life. So as a corollary, so the corollary is that in the cryptographic setting, the number of provers can be reduced to one. So what we get is what is called in cryptography a one-round delegation scheme, such that the running time of the prover is polynomial in T of n, and the running time of the verifier is n times polylog T of n. Okay, so this is the result more formally. So if you have a function that can be computed in T of n, in time T of n, and Bob offers to compute that function for Alice, Bob will be able to compute the function and will be able to convince Alice that the computation was done correctly in one round of interaction. So Alice just sends the input X to Bob together with some queries. Bob answer with the answer f of x together with some witnesses. And based on this interaction, Alice will be convinced that the computation was done correctly, and the running time of Bob is polynomial in T of n, so you don't, Bob doesn't need like to be infinitely powerful. It just needs to run more or less computation that takes T of n. The running time of Alice is very efficient. It's n times polylog in T of n, and all this under cryptographic assumptions, under the cryptographic assumption that Bob cannot break the encryption. But in real life, that's what you expect to happen, that if the encryption is good enough, then no computer can actually break it. So I will skip these two slides. It tells more formally what is the result in cryptography, because I only have maybe 2 more minutes. So I just want to mention that very recently we also had another application for our main result, for the multi-prover interactive proofs with no signaling strategies. And this is an application for hardness of approximation. Very roughly speaking, it shows that linear programming with pre-processing is quasi-p hard to approximate. But I will not get into this more. An open problem is what happens if the number of provers is constant. So as I said, in our result, the number of provers is polylog t, or if you think about the result for exp, the number of provers is polynomial. We know that you cannot do it with 2 provers, because with 2 provers it's known to be contained in p space. But the question is, what if you allow a constant number of provers that is different than 2, like 3 provers, 4 provers, or something like this? This is still open. We have no idea how to do that. Thank you.
Okay, thank you very much, Ran. We have time for 1 or 2 questions while the next speaker sets up. Thomas.
Yes. no. So you do need to interact with all of them.
Okay. And just another quick question. You sort of implied this, but so for the cryptographic results, so it's possible that we could go beyond exp, do nexp in the using the same transformation.
It's a very good question, and the cryptography people cannot decide if they believe that it's if they believe in that or not. So there are some results that show that kind of don't really show, but kind of suggest that maybe you will not be able to go to NEXP. But I never got into this result and see. So it's some obstacles that you have to pass. So my guess would be that you cannot, but I don't know. It's still possible that you can.
Okay, we have time for one more question.
I have a question. So you assume that the provers are very powerful. So can they just break the homomorphic encryption?
Okay, so that's a good question. I didn't go into the full definition of. I didn't go into the full definition of one-round delegation scheme, but yes, if the provers are very powerful, they are able to break the encryption. But you don't, for sure, in real life, you don't assume that they are so powerful. So you assume that they are powerful enough to do your computation in time t of n, but they are limited by some other bound t star of n that is much larger, can be even exponential, and they are limited by that bound, and therefore they are not powerful enough to break the encryption. So that's what happens in real life. You delegate the computation to a more powerful computer, but it's still a computer. It's not infinitely powerful. And very good encryption schemes cannot be broken by any computer, maybe even quantum computer.
Okay, thanks, Ron.
Thank you.